Hello friends, today's question. A container of large uniform cross-sectional area A resting on a horizontal surface holds two immiscible, non-viscous and incompressible liquids of density D and 2D, each of height h by 2 as shown in figure. The lower density liquid is open to atmospheric pressure, atmosphere having a pressure P0. So we have to solve these two parts, and each part A is having two subparts and part B is having three subparts. So in the first case, it is given a homogeneous solid cylinder of length L, which is less than h by 2, cross-sectional area A by 5, is immersed such that it floats with its axis vertical at the liquid-liquid interface with the length L by 4 in the denser liquid. Determine the density D of the solid, total pressure at the bottom of the container. So this is the basic figure. Each liquid has a height of h by 2 and we have two density D and 2D. So this will be our D dense liquid having a density D, and lower one will be 2D. And inside it we have a solid cylinder of length L, and it is given that the L by 4 is in the denser liquid, so the lower length will be our L by 4, and total length is given as L, so upper length will be our 3L by 4. And it is given that it is in vertical equilibrium, and this solid is having a density of capital D, which we are supposed to find out in part 1, and part 2 total pressure at the bottom of the container. Okay, so we start with part A. Subpart 1, and which says that density D of the solid, density D of the solid. So it is given that it is in vertical equilibrium, so therefore we can say that the weight of the solid will be balanced by the buoyant force. So we can say weight of the solid is balanced by the buoyant force so we can write this as that weight of the solid will be equal to buoyant force, and the weight of solid, let us call that as W. So W will equal to buoyant force, and let us call buoyant force as FB. So let us find out what will be the weight of the solid or value of W, and similarly let us find out what will be the buoyant force. So we start with the weight of the solid. Weight of solid, which is W, and that will be equal to our mg, and we can write this will be equal to volume multiplied by density multiplied by g, and this volume we can replace in terms of your length, and the area of cross section is given as A by 5 multiplied by D multiplied by G. So this is our weight of the solid. Similarly, we can find out the buoyant force. Buoyant force, that is our FP. Now in this case, the solid is, you can say, having buoyancy because of the two liquids having different densities. One is our 2D and another one is liquid which is having a density D. Okay, so it means it will be, one buoyancy will be of because of density D, another buoyant force will be because of density 2D. So we can say buoyant force FB will be equal to buoyant force because of density D plus buoyant force because of density 2D. So therefore we can write this formula as buoyant force because of density D. Let us call that a liquid 1. So this is our liquid 1 and this is our liquid 2. So buoyant force FB will be equal to volume displaced by volume of liquid 1 multiplied by density of liquid 1 and multiplied by G. Because buoyant force rises displaced volume of the two liquids. Okay, so we say displaced volume of liquid 1 multiplied by density of liquid 1 and multiply by G plus we have displaced volume of liquid 2 displaced volume of liquid 2 and liquid 1 is with density D multiplied by density of liquid 2 multiplied by G, and this is for density 2D. We substitute all these values, so we can say our buoyant force FB, the displaced volume will be of, you can say, the length of the solid which is in density 1 or sorry in liquid 1, that is 3L by 4 multiplied by area of cross section multiplied by its density and multiplied by G plus we have this our length of the solid inside the liquid with having density 2D L by 4 multiplied by A by 5 multiplied by density, that is 2D multiplied by G. So therefore, and this is our total buoyant force, and we already calculated our weight, and weight is our L A by 5 D multiplied by G, and we know that weight will be balanced by the buoyant force. So therefore we can write that our weight, which is our L A by 5 D multiplied by G, will be equal to 3L by 4 A by 5 D multiplied by G plus L by 4 cross section area A by 5 multiplied by 2 D and G. So length cancels out throughout, A by 5 also cancels out throughout, and G also goes away. So we are left with the density D, which is density of the solid, is equal to, here we are left with 3 by 4d plus, and this goes by 2, and this is left as d by 2. Therefore, we can say that the density of the solid will be equal to 5d divided by 4. So this is the density of the solid. This is the density of the solid. Now, so our part 1 is done. Part 2, total pressure at the bottom of the container. So we start with part 2, and part 2 we have to find out total pressure at the bottom of the container. Total pressure at the bottom of container. So in order to find out total pressure, we are going to find out total force, and simply solve, you can say manipulate with the help of area, we are going to get the total pressure. So the total weight at the bottom of the cylinder, total weight at the bottom of cylinder will be equal to total weight of the liquid and the weight of the cylinder. Will be equal to total weight of the liquids plus weight of the cylinder. Weight of the cylinder. So total weight at the bottom of the cylinder, we are going to call this as weight at the bottom with respect to cylinder, and total weight of the liquid, we are going to call this as weight total with respect to liquids plus weight of the cylinder, WC. So let us start with weight of the liquids. We are going to start from this part. So total weight of the liquid, weight of liquids, that is total with respect to liquids, and we have two liquids, liquid 1 and liquid 2. So for liquid 1, and liquid 1 is our lighter liquid, and the lighter liquid, it is having a density D, height is our h by 2, and cross-sectional area is our A. Cross-sectional area is equal to A. Therefore, weight of the liquid 1, weight of liquid 1 will be equal to A h by 2 multiplied by its density and multiplied by G. Similarly, we can do it for liquid 2, which is denser liquid. And its density is equal to 2D. Height of both the liquids is same, that is h by 2, and cross-sectional area is also same. Cross-sectional area is also our A. So therefore, the weight of liquid 2 will be equal to A H by 2 2D multiplied by G. Therefore, we can say that total weight of the liquid will be equal to weight of liquid 1 plus weight of liquid 2. We substitute the values. We write this as A H by 2 2D multiplied by G plus A H by 2, sorry, 2D is here, multiplied by G. And we simply add them. So we get total weight of the liquid will be equal to 3 by 2, and we have A H D G. So we got the total weight of the liquid. Now we are going to find out the weight of the cylinder. Weight of the cylinder, which is our WC, and WC is weight of the cylinder. And for weight of the cylinder, its density is given as capital D. Density is capital D, and its, you can say, height or length is given as L. Height is given as capital L, and its cross-sectional area is given as A by 5. So we can say our WC will be equal to A by 5 multiplied by L, and density is given as capital D and multiplied by G. And we already know relationship between capital D and small d. So we substitute here, we get A by 5 L, and capital D is our 5 by 5D multiplied by 4. So we get 5D multiplied by 4, and this is multiplied by G. And here 5 and 5 cancels out. So we get our weight of the cylinder is equal to 1 by 4 ALD multiplied by G. And so therefore, now we got both the values. We got weight of the liquid as well as weight of the cylinder. So we just add them. We are going to get weight at the bottom of the cylinder. So we can say weight at the bottom of the cylinder, that is WBC, will be equal to, we have this as 3 by 2 A capital H D G plus 1 by 4 AL D multiplied by G. And now we are supposed to find out the pressure. So therefore we can say pressure at the bottom of the cylinder, pressure at the bottom of the cylinder, let us call that as pressure at the bottom of the cylinder, will be equal to weight of the cylinder divided by area plus, total weight at the bottom of the container, and I think I made a mistake here. It is container, not cylinder. My mistake. It is asked for the container. So I wrote here as cylinder. It should not be cylinder, but it should be container. Okay. Weight of the rest is still correct. And weight of the cylinder, let us call this now Cy. Okay, now to differentiate this, therefore we can write this will be our Cy. It is cylinder, and rest is okay. Container is C. Yeah. Another thing, it is given that the lower density liquid is open to atmospheric pressure P0. So there will be extra term P0 in this particular equation. Pressure at the bottom of the container, not cylinder. So we substitute the values. We can write that our pressure at the bottom of the container will be equal to, we get this as 3/2 AHdg plus 1/4 ALdg divided by A and plus P0, and A cancels out throughout. So therefore we can write that our pressure at the bottom of the cylinder will be equal to, we just readjust the terms, and this will be giving us 1/4 dg, and we get 6h plus L. So this is the pressure at the bottom of the container. Please, C is a container. Okay, let me write it here. C is our container and Cy is our cylinder. And that would differentiate. And L is a liquid. L stand for liquid, and B stand for bottom, and T stand for total. So we found out our second part for part A. Now we are going to do for part B. We state that now cylinder is removed and the original arrangement is restored. A tiny hole of area S, which is much lesser than area of the cross section of the cylinder, of the container rather, is punched on the vertical side of the container at a height h. Determine initial speed of efflux of the liquid at the hole. So we have to find out three things. So it is given, this is the hole which is at a height h from the bottom of the container. Okay, so let me redraw this figure. So now we go for part B, and in part B it states that so these are the two liquids, H/2 and H/2, and here a hole is made of cross-sectional area S, and the height of this is small h from the bottom. So these are the liquids. This is having density D, and this is having density 2D, and because of this the liquid will start to flow something like a projectile. And in the first part we are supposed to find out the initial speed of efflux of the liquid at the hole. So we have to find out what will be the speed of efflux. So in this case, let us call this as point B, and let us call this as point A, and the velocity is given as, let us suppose this velocity is our VB. And let's define these terms. So we call that the velocity of the liquid at A is VA. So here it is a velocity VA, and at B it is called VB. we say VA is the velocity of the fluid at point A, velocity of fluid at level A, and VB is our velocity of fluid at level B. Velocity of fluid at level B. So therefore, we can write by the equation of continuity, which states that area of cross section of the container multiplied by VA is equal to S multiplied by VB. So from here we can say our VA will be equal to S upon A multiplied by VB. But in the question it is given that this area of the base of the container is very much large as compared to this cross-sectional area of S. So from here we can draw one important conclusion, that velocity at level A will be approximately equal to 0. Now we are going to use Bernoulli's theorem at level A as well as at level B. Using Bernoulli's theorem, which states that P plus half rho V square plus rho GH will be equal to constant. So let us modify this Bernoulli's equation for point A as well as point B. So we can say at level A, pressure is our atmospheric pressure P0 plus density is D and velocity is given as VA plus, and we have this as the rho GH. It will be having two parts. One will be density because of D and another one will be because of density of liquid 2D, and this will be equal to constant. So if we solve it, VA is equal to 0, so we get this as that P0 plus these two terms can be added up, and this will be giving us 3/2 dGH will be equal to constant. Similarly, we do for at level B. So we can modify, and in the question it is given the lower density is also open to atmospheric pressure. So once again the P will be equal to P0 plus there will be half dVA square plus half 2d VB square plus 2d GH is equal to constant. So VA is equal to over 0. So we can write this as P0 plus this becomes D, 2 and 2 goes away, VB square, and plus we get this as 2dGH is equal to constant. So these two equations are for level A and level B. Therefore, we can say, thus we get P naught plus 3 by 2 dgh is equal to P naught plus d vb square plus 2d gh. P naught and P naught cancels out, and d and d goes away. So we are left with that our 3 by 2 gh will be equal to vb square plus 2gh, and this can be written as that vb square will be equal to 3 by 2 gh minus 2gh. Therefore, we can write that velocity of a flux at point B, that is Vb, will be equal to g, this comes as 3 by 2 h minus 2h, and it comes as square root. So this is the velocity of a flux at the hole. This is the velocity of a flux at hole having cross-section area S. So we were able to solve part 1 for it. Now we solve part 2. And part 2, it is supposed to find out the horizontal distance traveled by the liquid initially. Okay. So we solve part 2. And for that, let us draw, this is our point B, and liquid something like this, a shape of projectile, and its height is given as h, and let us call the horizontal distance is x, and the velocity of a flux we just calculated is Vb is, now we can say that the horizontal distance will be equal to the velocity multiplied by time, and we can find out time. So let us start with the time. Therefore, we can say that time taken by the liquid to fall through the height h. Time taken by the liquid to fall through height h, and we already know that formula, that T is equal to 2h by g. So therefore, the horizontal distance will be equal to horizontal distance, which is our x, will be equal to Vb multiplied by time t. We simply substitute value of Vb here, t also. So we get x is equal to, Vb was our g, 3 by 2h minus 2h square root multiplied by 2h by g. G and g cancel out. So we can write this as that x will be equal to, and we can take 2 as LCM, so this becomes 3h minus 4h, and 2 and 2 also cancel out. So we can write this will be equal to our h, we have 3h multiplied by 4h and its square root. So this is the horizontal distance traveled by the liquid initially. This is the horizontal distance traveled by the liquid initially. And this completes our subpart 2, and we've now come to the last part, the height hm at which the hole should be punched so that the liquid travels a maximum distance xm initially. Also calculate xm. So we have to find out the height hm so that the liquid travels the maximum distance xm, and we have to find out our xm. So we just calculated our x. So let us start with subpart 3, and if we say we have to find out h, so we say to find height h at which x is maximum. So which basically means we simply derivate our maximum, the distance x with respect to h, and put is equal to 0. So we substitute the value d of dh, and this is our h, 3 capital H minus 4 small h, and whole raised power 1 by 2 is equal to 0. And now it's quite simple. This will be giving us, we multiply this comes as 3h multiplied by h, and this is 4h square, and this is 1 by 2, so 1 by 2 minus 1, this will be minus 1 by 2, so it will become in denominator. So we can write this as 1 by 2, and square root, this becomes our 3h minus 4h square. And now it's derivative comes, now this derivative will be 3h minus 8h is equal to 0. So from here we can say our 3h minus 8h is equal to 0, and this gives us that our 8h is equal to 3h, or we can say h is equal to 3 by 8 capital H. So x will be maximum at this height. Therefore we can say x will be x maximum at h is equal to 3 by 8h, and we are supposed to find out the maximum value also. So we can say the maximum value of x max will be equal to, we substitute value of small h as 3 8 by h, so this comes 3 8 by h capital H, sorry, so this becomes 3h minus, and we have inside 4 multiplied by 3h divided by 8 and its square root. So it's quite simple calculation. This directly we can write that x max will be equal to 3 by 4 times capital H. So this completes the our third part also. This question no doubt was quite lengthy, but quite simple, directly based on the equations. Certain things to be kept in mind, that first is the lower density is also open to atmospheric pressure P naught. So this P naught will be also coming into the lower part here also. Okay, rest is quite simple. This completes the question. Thank you.